Okay, just a reminder on what was due today is there was watching a structural engineer and architect video and then answering some questions about it. And then there was that little assignment on the forces. What was your thought about that video?
It was educational, that's for sure.
So I think back to my career, and that is not like a made up thing for YouTube. That's the way that I would meet with my structural engineers if I was doing something complicated. Now, if obviously it was a simple house where, he was doing a complex, it wasn't a complicated house, but it wasn't a standard construction house, right? It was on this island with rocks and they had it up on piers and then they had to cross brace it. So like on a typical house, I wouldn't sit down and have a really intense meeting with that. But if you're trying to do something out of the ordinary, you do want to have a meeting where you and the engineer are on the same page, because especially where the structure is exposed, what they do impacts what you do or what it looks like. So the other thing is you guys did a good job on the structural failure case studies. Now it's meant to be sobering, but not scary. So it's sobering because we're not just like painting walls one color versus another color where there's no implications. In the business that we're working with, we're dealing with public safety. And that's why the government's involved is like, you can't go out, even though you're an architectural technology student, you can't call yourself an architect. The government is involved with who can stamp plans, do engineering calculations. The government is doing that because if they didn't do it, it would be public safety. Just because like you can't have your random person on the street put out a sign and say they're a doctor and start prescribing medicines and doing surgeries. You can't have your average person off the street put out their sign and say they're a structural engineer or say they're an architect and start designing structures that impact the public safety. So we're going to get into we kind of got our introduction out of the way. Now we're going to start to work from the ground up on how a building gets structured. So just a reminder, we have those two assignments. We're going to have some class time to practice on the assignment. So there's like a practice assignment, and then we're going to have an assignment on sizing footings. And then we're going to, next class, we'll learn how to do a footing and foundation plan. Okay, so that's my overall plan here. So I'm just going to show you my agenda for this week. So here's my agenda. Pretty simple. I do a PowerPoint to kind of give you an overview on footing and foundations. I give you another PowerPoint on how to size column footings. And then we'll work practice footings sizing with a partner. And then I've got a key that you can check your answer done. And then when you have it down, then I'll give you the assignment and you can work on the assignment that you actually get graded on. My guess is we're not gonna have enough time to start about the footing and foundation plan. We'll just move that to the next class, but we'll play it by ear and see how it goes. Okay, so it's not a super complicated agenda for this week. So let's get right into it. Let's look on footings and foundations. Make sure I've got everybody on my attendance. This is Alex here. No, he's not. Okay. So I don't want to show that. Any of you ever poured footings and foundations? You have? No? Okay. So I kind of like this picture in a way because it shows a couple things here. So this is probably a walkout basement, where the foundation has to step out and we're at the lower level looking up the hill. Couple things I wanted to point out. Now you'll notice like when you dig a step in the dirt, you can't dig a 90-degree step because the dirt would like collapse down. It's not like you're working with a solid material. The dirt's got what they call a level of repose or an angle of repose. So you can't cut, everybody kind of understand that if it's loose soil, if it's not like clay, you can't cut a 90-degree angle in and expect it to stay. It'll mush out. So what happens is as they dug this in different levels for the steps, they've got like this angled part here and this angled part here. Now there's two different ways of doing it. And I've seen both ways in the site. I have an idea that one way is better than the other. So one way is they just form it up like it's cut at a 90-degree angle, and then they just kind of try to pack dirt in underneath the area where it's at a 90-degree angle. The other way of doing it is saying that, okay, we know that we can't really pack dirt in at the right compaction there. So we're just going to pour the bottom of that footing at an angle to match the angle of the dirt. That's the better way. Now, why don't people do it that way? Because it uses more concrete, right? Because now I've got to do all the concrete here that's missing from here. But it's better structurally because you need that dirt to be compacted. You can't just like blow a little dirt in there and then expect it to take as much load as dirt that's been there since the creation of the earth, right? Because that's already been compacted over thousands of years. Okay. The other thing I wanted to point out is there's an OSHA safety problem with this drawing. What is it? Yes.
Odds need covers on.
Yeah, so if you ever go by a construction site, and they've got, looks like little orange tennis balls or golf balls on the top of all the rebars. That's an OSHA requirement. And the reason is, look at that, there's all kinds of boards and stuff, there's rocks around there. What are the odds that somebody's be walking around carrying something, they're gonna trip over a board and they're gonna fall on the rebar? It's not zero, right? It's got a chance of happening. So the reason they put these orange plastic balls on top of all the rebar is that keeps it from punching through your body when you fall on top of it. Because a little 1/2-inch diameter rebar with your whole body weight going on it will literally punch into you. So that's an OSHA requirement on that. Okay, so let's keep rolling here. So working from the ground up, the bottom part of a building is called a footing. So it's the lowest part of the building. It's the part that where the building's load, the gravity load gets transferred to the dirt or the earth. So the footings are typically wider than the foundation wall or the column above. So that's to spread the load over a larger area. If we somehow had a building where we have a building load that's more than what the soil's bearing capacity, the building actually sinks down into the ground because it's putting that load on a very small area of soil. So we want to spread it out so that if the soil can take 2,000 PSF, we have to spread that load out so that it's 2,000 PSF maximum. Does that make sense? The way that in our climate that you can kind of visualize this is have you ever tried walking through really thick powdery snow and you sunk down into it? That's what your building theoretically would do is if your footing isn't big enough. So on certain conditions, you can put snowshoes on and walk on top of the snow and spread your load out over a bigger area of snow so that you don't punch down into 3 or 4 feet of snow every time you try to walk through it. You can walk on the top. Now, I have to tell you that when I was younger, people had snowshoes and everybody had snowmobiles because we had so much more snow. Now, I know the climate's changing. We're not going to get into why it's changing, but it's definitely changed over my lifetime because like snowbanks 5-6 feet high all winter long, snow all the time. Everybody had snowmobiles, everybody had snowshoes, cross-country skis. It's not quite like that anymore. We do get snow, but it's not near the depth. So maybe you've never used snowshoes, but just take my word on it. If you spread that load out, you don't sink down into the snow as much. Any of you ever used snowshoes? Okay, I see lots of people know about that. Okay, so we have 2 different kinds. There's one that's footing that's under a wall, and that's called a continuous footing or a strip footing. And then it's also called a wall footing, as you see on the diagram. And then you can either have an isolated column footing, or they also call them spread footings, which are under piers or columns. And those are the ones we're going to be sizing in our assignment today. So they're typically poured concrete, and they're reinforced with steel rebar. so the houses typically use 2 number 4 continuous. Now this one looks like 3 number 4 continuous, so it's got 1 row here, 1 row there, and 1 row there. And so when they say continuous, they overlap them. They don't have like one piece of rebar that goes around the jigs and jogs, but they overlap them and they tie them up with wire ties to keep them together. Then house spread footings, they typically put 2 each way, 2 number 4 rebars. Now, when I say number 4 rebars, each number is 1/8 of an inch. So if you have a number 4 rebar, it's 4/8 or a 1/2 inch diameter. If you have a number 5 rebar, it's 5/8 inch diameter. So you're not being tested on that, but that's just a little way you can visualize. If somebody's telling you they got a number 4 rebar, you're like, oh, 1/2 inch diameter. That's a very common size in residential construction. And then these are like L-shaped rebars, and they cast those into the footing like you saw on the first slide, and then they pour the wall on top of it. So those L-shaped rebars tie the foundation wall into the footing when they pour that. So if possible, we want our footings to be on undisturbed soil. Have any of you ever like dug a big hole in your backyard and you had this big pile of dirt in your backyard and you were gonna take it somewhere or use it somewhere and you never did, and it like over 6 years, it went from a pile when you first dug it and you threw it on the pile, it was like 6 feet high, and then over the years as the freeze and snow and it got rained on, it ended up being 3 feet high because it like the weather will compact it down. Now the dirt that we walk on has been here for thousands, I don't know how many thousands of years, and it's already been compacted, right? It's gone through freeze-thaw cycles. But when you dig a hole and you just pile it up somewhere, it's all fluffy. Have you ever like baked a cake and you packed the flour into the measuring cup? You're not supposed to do that because your cake will get too much flour in it. It's supposed to be light and fluffy. It's the same sort of thing. You can pack that soil down into a smaller area and it's much more compacted. We don't want to build our houses on fluffy soil. So that's called fill when we bring in soil that hasn't been there for 1,000 years. And here's where it can be a problem. So imagine you're building on the side of a hill and you want to make a level area. Now, in order to avoid having to bring in a lot of fill or having to dig into the hill a lot, economically, it's good to balance cut and fill. So this is the cut where we're digging out of the hill. And this is the fill where we're taking that dirt and making a level area. So you see, I'm making a nice level area. And if this area equals this area, I don't have to pay to bring in dirt, or I don't have to truck dirt off of my site. Does that all make sense? I'm balancing where I'm cutting out of the hill and where I'm filling to make my level building pad. Now, what's the problem with this? The problem with this is this soil here that's been dug into the hill has been compacted for thousands of years. It's as compact as it's ever going to get. This is light and fluffy because we just dumped it off the side of the hill. So the problem is if we put our house on that, the part that's on the fluffy part will want to sink down, and the part that's on the 1,000-year compacted stuff won't sink down, and the foundation will literally crack where it, part of it will come down. So how do we avoid that? Well, we have to compact that soil so that we're artificially going in and compacting it with a machine to make it as compact as the normal soil is. Now, there's a couple different ways of compacting. One of them is they get these like rollers and they like actually vibrate. So if you're ever near a construction site and your house is like vibrating, they probably have one of these big roller compactors that they, like a steam roller they used to call them. They roll along and they compact while they're rolling it. The other thing is this is called a jumping jack. And when I worked in a design build firm, they made me go out on the job sites. And this was one of my jobs, was running one of these jumping jacks. Cause I think it was like it's kind of a pain in the butt. Cause if you get it off thing, it tries to jump at an angle way and then you got to hold it up. But that's how they compact it. And so what they typically do is they put like a foot down, run the compactor over it, put another foot down, run a compactor over it. Because that's how they can get it compacted evenly all the way up, even if I have like 8 feet of fill. Okay, so that's that. So obviously on a day like today where it's below zero, we have a below zero wind chill. if like Fluffy the cat dies and you want to go out and dig a hole for Fluffy the cat, it's gonna be like concrete. You cannot literally get a shovel into it. You can dig into it, because that ground freezes. And it gets very hard because that frozen water in the ground freezes in the areas between the soil, and it gets like hard as a rock. So in our climate here, these are the frost steps. We have to get our footings below frost in order to minimize. So what happens in the winter when it freezes, that water expands, and when the water thaws, it shrinks. So that building, if it's on that frozen water in the frost area, it'll actually go up and down. And you see this a lot on farm buildings, because a lot of farm buildings, they don't put frost step footings on them. So I worked on, my parents had a farm, and we had doors that would not open in our buildings in winter where they would in the summer, and vice versa, because the ground was heaving, the doors were going up and down in relationship to the dirt. We also had a crack in our in our garage where in the winter where the ground froze, we had like a 2-inch crack that we had to drive over to get into our garage. And in the summer when the ground thawed, it would straighten back out. So we can't put our buildings on ground that's freezing and thawing. We got to get below that frost step. So in the Wisconsin code, they require the footings to be placed below 48 inches. So they got to be 4 feet minimum below ground to the bottom of your footing. Now you can go lower if you want, but you can't go less than that, because they don't want these buildings going up and down. Because if we have doors that's swinging out and the building goes down in relationship to the grade, the door won't open up. If it goes up in relationship to the grade, now instead of being wheelchair accessible, now I got a 2-inch thing there that a wheelchair can't get up. Okay, so we want our buildings to be level, so we got to get our footings below frost. Now, does frost ever get below 48 inches, even in the lacrosse area? Yes, it does. So areas where there's traffic and where they take the snow off it so there's no insulation, and if it gets really cold like this, the frost will go down lower than 4 feet. And that's why you get like frozen pipes and that break in the winter. It's like the snow acts like a blanket to insulate the ground. So if it gets really cold with no snow, like we don't have much snow and it's supposed to be cold for a while. My guess is if you were borderline on where your plumbing pipe was, you might get that frost going down low enough that it's going to start to freeze and break pipes if we have a really long cold snap without much snow on the ground. Okay. So when I talk about frost steps, it's a code requirement, but it's based on reality, which is we got to get our footings below that frost steps. Any questions? I've gone through 5 slides. Okay, I've got 15 more. So I talked about this on the first slide. I believe the proper way of doing this is to run the bottom of your footing at the natural area of grade if you're stepping down. It is not to do this because this requires you to somehow get good compaction. Like this little part here is bearing on undisturbed soil, and this part here is bearing on undisturbed soil, but this part is bearing on disturbed soil that they just tried to pack underneath there after they poured it in 90-degree angles. So a lot of times when I would go on job sites, I'm like, well, why didn't you just not do that? I didn't draw it that way. Why did you do it? Well, they didn't want to spend the money for the extra concrete. So what the excuse I typically heard was, well, we're going to do water compaction. So that means they put a bunch of dirt in there with shovels and they hit it with a hose. And they put some more dirt in their shovel with a hit in the hose. Well, that's okay, but it's not as good as a full compaction. It's not as good as this way here. So you might see both ways in your career. So the reason we step footings is as that grade slopes down, say we got a walkout basement and this grade's going to continue to slope down, we have to keep stepping our footing because it's got to keep being at least 4 feet below ground, below the top of the ground for frost protection. So as the ground slopes down around your house, your footings have to slope down to stay a minimum of 4 feet underneath. So like this distance here to here has to be 4 foot minimum. And if we would keep running that footing straight across, eventually the footing would be right at ground level and it wouldn't be 4 feet below frost. Okay, so let's talk about the bearing capacity of soil. So in a commercial project, almost always you'll have what's called a geotechnical report, or informally, it's called a soils report done. And these are specialized people that go out there with specialized drills and they figure out what the soil is and how much load in pounds per square feet it can take. Now, if your client won't pay for a soils report, it's not a bad idea to go out and talk to other people, and like if they're building a lot of houses around you, just see what the soils are like, talk to other contractors. Because you might find out, for example, that if you dig down 4 feet, you hit water, so everybody's setting their house higher than they normally would, because there's a layer of clay that's keeping the water up there. So I'm going to show you on this next slide here what a soils report, how it's done and what it looks like. So they do like a hollow core, and they core down into when they drill down, they're not just drilling and forgetting what they're drilling through. They're actually saving core samples as they drill down, and then they pull it out, they analyze it, they take samples of it, they test it in a lab, and they figure out how much load it can take. So, for example, on this one, just because you walk around and it looks like good dirt, it doesn't, you have no idea what it's down. Like say your foundation on a commercial building is 10 or 12 feet below the natural grade. You have no idea what's down below you, right? It can be beautiful dirt all the way down. It can be sand all the way down, but you can dig down 5 feet and you can find a bunch of rotting tree stumps and peat, because it used to be an old marsh and it's got a bunch of rotting vegetation underneath you. So for example, this one here is clay with decayed roots and iron staining. This has got brick made ground. So this is probably stuff they filled in on top of the old marsh that was there, which has got brown sandy clay with brick fragments and rare cobbles. So like when they tore up the street, they're like, hey, dump it in my lot. I got this marsh I want to build on. And then the next layer down here is soft, dark brown peat with frequent roots and high organic content with some solid wood. Now, do we want to build our houses on decaying vegetable matter? No, we don't, because it's going to keep decaying and decaying and decaying and sinking down. So around here, you can run into peat because we've got like marshes and, little old lakes that used to be there. And I know that's what my name is, but peat is bad for buildings. We don't want peat, our buildings to be in. Okay, so I'm going to tell you 3 examples of why, in my career, why soils reports are a good idea. I was working up in Wausau. We were building a building near the top of a hill. I talked to the owner and the contractor, and this was a medical building that we were doing an addition onto. They said, well, no, we'll hit rock a few feet down, but it'll be soft rock and easy to remove with an excavator. So they didn't listen to me and they refused to pay for a soils report. Like if the owner has to pay for the soils report, I can't force them to pay for the soils report. If they're too cheap to pay for it, they just don't pay for it. So we designed the soils based on worst case scenario, 2000 PSF, which is the lowest bearing that you can typically do. But we just believed them that we're going to hit soft rock. Well, what happened was, where you put an elevator and you got to dig down even 4 feet deeper because the elevator's got a pit in it. And so when they started to dig for the elevator, there was this vein of very hard blue rock that required a very expensive special equipment that they had to get, it looked something like this, but it had like a tungsten diamond point on it because that was the only thing that would break this rock. Because it was like next to a building. We couldn't just drill holes in it or next to it and put dynamite in there because we'd have blown up the existing building. Now, the other goofy thing, which I never would have believed, we're on top of a hill. We're digging down 10 feet. Next to this vein of blue rock, there's an underground river running through the rock. And so I'm like, we're on the top of a hill. How can there be a river running 10 feet down through solid rock? But there was. So we had to deal with the water coming into our elevator pit. So this all costs extra money and delayed construction. Now, if we'd have done a soils report and we would have punched a boring down where our elevator was going to go, we would have at least known what the problem was. And the other thing was, we might have decided, hey, let's try to punch a hole on the other side. Maybe we'll redesign our building so we don't have to go into the underground river here and we'll go on the other side of it. But they didn't listen to me, so they ended up taking a risk and that came back and haunted them. Now, you're gonna see a pattern here. I don't know what it is, but people, if money was at stake and I told them to do something, thought they could save money, oftentimes they wouldn't listen to me. So here's another example here in the La Crosse area. I'm not gonna name the building, but I could. Why do we need a soils report? Again, the owner and the contractor both said that they were adamant about it. They know this whole area is sand 20 feet down. Because this is an old river valley. It used to be, it's sand, sand, sand. We're not gonna have any problems with soil. So they dug down sand, sand, sand. Then they got 6 feet down and there was a layer of impermeable clay and it had water sitting on top of it. And the reason it had impermeable clay is back thousands of years ago, that was a little lake or a little marsh or something. And the clay had built up and that's what kept the water from draining down into the sand. And so what happens if you've got this huge area, like miles square, that's got this impermeable clay layer with water sitting on top of it? What happens when you punch a hole in it? All that water wants to drain down into the hole that you just punched into it. So they're trying to dig for the foundation of water, water, water. So basically you just have to keep pumping that water out until you've drained all this water that's been sitting for hundreds of years on top of this impermeable clay layer. So this also cost extra money and it delayed construction. Now, this is not a picture of the job site, but that's kind of what it looked like. And then the last one I'm going to talk about, and this is one where we actually did a soils report and we knew what we came up with. I used to work on that River Architects at the end of 7th Street, that big silver building, kind of at the end of that cul-de-sac. If you ever go down to get to the bike path there, there's that big silver building at the end of 7th Street. Well, believe it or not, that lot that we bought, when we did the soils report, there's marshes all around it, right? There's a marsh to the left, there's a marsh to the right, you know, because the rivers go through there. The part that we were on used to be a marsh, and then they filled it in, put a junkyard there. Okay, so we were on fill on top of peat. Because the peat is like all the cattails and the algae and everything that's in a body of water. It falls to the bottom, but it doesn't totally rot. It kind of makes this spongy organic matter. If you ever walk through a marsh, you're kind of walking on all this dead and decaying vegetation down there. And so what happens is that stuff keeps decaying very slowly over time, and you can't rest your building on it because it's going to sink down and down and down. So it was very good that we did a soils report there because we at least knew what we were dealing with. Okay, so here's a chart from the Wisconsin Uniform Dwelling Code. So this gives you the various soil bearing capacities for different kinds of soil. So if you can identify the soil, the code lets you go with these, but you see the lowest is 2000 PSF. So when I don't have a soils report, like some soils around here, they'll go to like 2500 or 3500. But if they don't do a soils report, I would assume 2000 PSF to be safe because that's typically the minimum that you can do. And I checked with the building inspector. Houses typically don't get a soils report and footings are typically sized for 2000 PSF. So I talked to that chief building inspector in La Crosse and that's what they told me. Commercial, you typically do get a soils report unless your owner is too cheap to pay for it. And they'll tell you exactly what the allowable soils bearing capacity is. Got to be cautious on areas near water because they might have organic soils, and that means peat. Vernon County, any of you live in Vernon County? Vernon County, none of you, okay. Vernon County is notorious for having poor draining clay soils. Around here, it's rock, it's sand, because this was all like in this immediate area was the river valley at one point. At one point, there was water from the bluffs there to the bluffs there, and it dumped a lot of sand. So a lot of this is sand around here. Vernon County has very poor draining clay soils. And if you buy a house in Vernon County, make sure you don't have water in your basement because a lot of houses in Vernon County got water in their basement because the soils around there, they're like almost like a swimming pool liner. That clay is so tight that it won't let water drain through it. So let's talk a little about foundations. So most of you probably grew up on a house with a basement, and a basement is usable space under the first floor. And some of you might have grown up in a house with a crawl space. So a crawl space is typically like, hey, I don't really need a basement. I'm only got to go down 4 feet for frost, so let's just go down 4 feet and call it a day. They still let you have that space under the first floor so you can get to your plumbing piping if it leaks, or if you can get to your, put your mechanical ducts in there or whatever, and maybe run electrical down there. But it's basically built like a basement in most cases nowadays, except it just has less headroom. Now, personally, I hate crawl spaces. I hate them, hate them, hate them. You already got to dig down 4 feet to get below frost. It doesn't cost that much more to dig 4 feet more down and have a full basement. Basements allow you to store stuff in them. They allow you to have workshops or other uses down there, play pool down there, whatever you want to do. If there's a tornado, you can go into the basement easily. If the people are having to fix your plumbing or your heating, they're not crawling around, hitting their head on in the crawl space on the floor joists because they've only got 3 feet of headroom. So I detest crawl spaces. I would never recommend my clients do a crawl space. It is not worth. You're going to get so much more resale value. It's going to be so much more nicer. The only reason you don't want to do a basement is like, say you've got groundwater 5 feet below and you're worried about getting water in your basement. But if you had a crawl space 4 feet below, you wouldn't get water in your crawl space. Yes.
These are very compelling statements. Do you argue with Jay and Josh about it?
I was just gonna ask that.
Excuse me?
I said, these are very compelling statements for being pro basement. They are very anti-basement. Do you argue about it with them?
The thing is if you ask, like me and Tim and me and Josh, some things, we are going to not agree because it's not, I'm giving you my reasons why I like basements. And I hate crawl spaces. I'm assuming he hates crawl spaces because nobody in their right mind would like crawl spaces. Now, between basement and slab on grade, that's a bit, I can understand why somebody would just want a slab on grade and not a basement. I know Josh's arguments against basement. As a professional residential designer for many years, you are not going to talk most people out of basements. Okay. And you're saying the same thing, right? Your clients want basements. So I know there, in the building science world, there are some problems with basement, but typically they can be at least managed or dealt with. So in my mind, if you're going to do a basement, you do it right. You do the waterproofing right. You do the insulation right. You do the radon mitigation right. You do the drainage right. So my take on it was do it right if you're going to do a basement.
We got many a lesson on the evils of basements with Jay.
Oh, Big J hates basements too?
Yeah.
Okay. Well, okay, so I'm not saying I'm right and they're wrong. I'm just saying I have a valid case and they probably have a valid case too. It's up to you to decide. I don't want to make it sound like I'm the voice of God because that you can't argue with me because other people have valid concerns. It's just a matter of in the real world, in my mind, you're not going to get away from basements because they make so much sense and clients want them. So you better just know how to do them right. Okay. Slab on grades. I have zero problems with slab on grades. You're have no space though underneath your slab, and you still have to either do a frost wall or you have to do a frost protection footing, and we'll get to that later. The downside with slab on grade is something goes wrong with your plumbing pipe that's underneath the slab. You're there with a jackhammer. You're not walking into your basement saying, "Oh, the pipe's leaking there. I gotta fix this joint." You're there with a jackhammering up your slab, trying to figure out why your water's leaking or your sewer's leaking underneath your house. So slab on grade's got advantages to it, but it's got disadvantages as well. Okay, so let's talk a little about slab on grade. The first one I'm talking about is you got to dig down 4 feet anyway. So you're gonna have to dig a 4-foot foundation wall around it, and then you have your slab on grade. So the distance between your finished grade and your bottom of your footing has to be 4 foot minimum. Now there is such a thing as called a frost protected shallow foundation. So the reason we're having to go down below frost is that we are concerned about that frozen ground thawing and freezing and moving our house up and down. Well, the way that we stop that by not having to dig a frost wall is we put insulation way out to keep that cold from the outside from getting in underneath our building. So the ground's always at 50 degrees and our building is, obviously it's not, 100 below or 50 below zero or whatever it is in our building. So there's some heat here. So if we put a layer of insulation under the dirt, it will keep that cold from coming down and freezing that area directly under our building. And then we don't have to worry about our building going up and down. Now, in theory, you can do this on houses. At least when I was working, it was never done on houses, but a lot of times it was done on garages. Okay, so they would do it on garages. Real world, are you seeing this at all on garages or on houses or on both?
I've seen it on both.
Okay,
I might actually have pictures of it.
okay. So it's becoming more and more and more common. But again, when I was doing houses, it was not common on houses. It was more common on maybe a garage. So now let's talk about how we make foundation walls. So in my opinion, the best foundation wall is a poured in place concrete wall. And there's different ways you can form up that wall. You can have wood forms, aluminum forms, or insulated concrete forms. We'll deal with that on the next slide. Concrete block is the other probably most common material in Wisconsin. Now around here, I see more poured concrete, but if you go to Milwaukee, they had a very strong Mason community and Mason unions in Milwaukee. And they were very cost effective doing block foundations. So you see a lot of block foundations in Milwaukee on the eastern part of the state. Now, those of you that know what your foundation is, let's have a show of hands. How many are concrete? 1, 2, how many are 3? How many are block? Where you see the lines? 1, 2, 3. Okay, so it's about 50-50 or 4. Concrete block is okay, but in my opinion, it's not as good as a poured wall because all these mortar joints are weakness planes. And then there's something called permanent wood foundation, where they actually don't put any concrete below ground. They just make it out of studs and they have like pressure treated wood and they hope their waterproofing holds up as long as the house does to keep these studs from all rotting. We've already heard from Shane on our mold side, but he dealt with one of these houses where it actually rotted out. So I am not a fan of permanent wood foundation. If I had a client that insisted on one, I would say get somebody else because I'm not going to put my name on it. Because in my view, if I'm doing a house, it's supposed to, the part in the ground should last for at least 100 years because there's plenty of 100-year-old houses around here that they've remodeled and they fixed, but you don't put wood below grade. I just have a problem with it. But I have met some people that were so into climate change that they're like, concrete puts a lot of carbon into the environment. We don't want to have any concrete on our house. We're just going to have concrete on our basement slab. We're going to do a permanent wood foundation. And this was their dream house. And I'm like, yeah, I don't think it's worth it. I think poured concrete is the way to go. Okay, so let's talk about poured in place concrete. You need to put formwork up. So it's like a cake pan when you make a cake. You need to hold the concrete in the shape that you want before it cures. So this is showing wood forms. And then you need to place the concrete. So this is showing a chute that if you can get your truck nearby, otherwise they use pumper trucks, which is what's showing here. There's like a big boom that comes out that you've probably seen, and they fill up the walls with that. Or if things are really bad, you can't get a truck or a boom truck, you can literally have ramps with wheelbarrows, and that's pain in the butt. You don't want to do that. If it's not engineered, there's an 8-inch minimum thickness by code for basement walls. Okay, so let's go on. Insulated concrete forms are like adult Legos. So you stack these things up. They're pieces of plastic that are embedded in layers of expanded polystyrene. And those expanded polystyrenes have little like Legos where they interlock with each other. And then you can put your rebar in there, so you can see this green stuff is rebar, and reinforce the wall, and then you can pour it up. Now this is becoming more and more popular. It's a great system. Oh, here are those OSHA caps on the rebar. So you can see this job site is complying with OSHA. These little orange things there. So I think this is a great system. It's becoming more and more popular. Have you seen it on any jobs?
Oh, yeah.
Yeah, you haven't. Okay, so it's becoming more and more popular, and you don't have to do just your foundation. You can do your whole house all the way up to the, the roof with this stuff. It's a really nice system, and it's really great for DIY builders, because I ran into a lady when I got hired here that was the HR person that helped me with my paperwork. She was about my age, and she built her whole house herself, stacking up ICF forms. And she just had her nephew and his friends help her when they poured it, and she built her whole house herself by just stacking up these adult Legos. And then had some help for the pouring of it, and then she could, she had the walls, everything up, and it's solid. It's got a lot of advantages to it. Okay, so concrete masonry units, we end up with a concrete wall, except it's concrete block, and we don't have to have formwork. So if we can't get a truck in, and all we can do is like pick up a block and carry it and put it on our wall, well, then it makes sense. I don't think it's as good as concrete, because the mortar joints are always weaker than poured concrete. So there's always weakness planes if you've got like too much water making soil pressure on the outside of your house. I've seen a lot of block walls that have caved in or cracked into the house because of soil pressure, or like a big construction machine driving too close to the concrete block. Now, if you want to make it super strong, you can fill all the cores with concrete, and then it kind of becomes like a concrete wall where the concrete block is the formwork. What's another name for concrete block? Concrete masonry unit. So a lot of times in the field, you'll hear it called CMU. So here you can see there's some rebar down on the floor. What are those white snaky things there? What do you think that is? In-floor heating. So if you want to have your floor in your basement nice and toasty warm, they take these plastic pipes and then they run hot water through that to warm up the concrete. Okay, one more slide after this one. As we mentioned before, water is a huge problem in basements and crawl spaces. So if you're going to do it right, you need to make sure you keep the water out of the house. So there's two ways you can get water. One is surface water. That's the water that falls from rain or drains off your roof. That's the water that hits on the surface. So in that case, we either have downspouts that kick the water away from our house. We slope the foundation away. We slope the ground away from the foundation. So that lets all that surface water get moving away from the house so it doesn't stay up close to the house. There's other ways of getting water in the house, which is a water table. So like the water has a certain level that if you dig down far enough, you'll hit water. So like if you get closer to the river, if you dig down far enough, you're going to hit water. And sometimes it's not at the level of the river. Sometimes it actually comes up a little from where the level of the river is. Just the pressure of that water goes into the soil. I know I did a project where our office in Madison was on the isthmus between the lakes and Madison. And we had a little river running through the basement of our building. It's an old 1880s building. And that's because there was a high water table because we were on that isthmus where the Capitol was, surrounded by lakes on all sides. And so that water actually, if I draw a little sketch here. So here's the lake. Here's the isthmus, exaggerated. Here's the lake. Here's the state capitol right here. Here's where our office was. That water, you would think that, well, we're above the lake, so that groundwater is going to be there. The groundwater actually can follow the slope of the land. It kind of gets pressed up there, and it kind of fills in the voids of the soil. So in our building here, we had a little permanent little river running through our basement, because that groundwater was up high enough that we had water running through our basement. So if you have water down below and you're worried about it coming into your house, you should have waterproofing under your slab. You should have waterproofing on the outside of your foundation. And then you should have drain tiles, which take that water that's trying to come up, or it's coming down from the rain and stuff outside, and it makes it so you can get it away from your house so you don't have to worry about it getting into your house. Now, the people that are basement haters, one thing I will agree on, carpeting in a basement is not a great idea. Because what happens is that basement sweats even if it doesn't get water because it's cooled. Remember the condensation I talked about last semester in building materials? You don't want typically carpeting in your basement. The other thing that's a bad idea is if you're going to do a basement and insulate it, it works better if your insulation's on the outside versus on the inside. And if they talk about it in Josh's class, the right way to do a basement, in my opinion, the right way to do a basement is to put the rigid insulation on the outside, not on the inside of the foundation. Okay, so now my last slide is, okay, now we've got these pipes where they're pipes with holes in them that the water's gonna drain in. What do we do now? We got this pipe filled up with water. What do we do with it? So what happens here is that we have these pipes go through the footings and they go into a sump pit in your basement. So have any of you gone into your basement, you've seen this thing with a cover on it, or maybe there's no cover on it and it's got a couple pipes coming out of it or one pipe coming out of it? That's a sump pit and it's got a sump pump in it. So this is where the water comes in from those footing drain lines and it starts to fill this up. This is just like the float in your toilet. Once the water gets to a certain level, that float kicks in and it pumps this out here. And let me see if I can. So what happens is this gets pumped up to above grade and then it gets spit out. And there's typically like a flexible pipe that gets it away from your house because otherwise it would just drain back down and the cycle would go over and over again. So if you ever walk by somebody's house and there's this flexible pipe coming out of it and water's gushing out of it, that's probably what's happening. Their basement, if this pump wasn't there, their basement would start to be filling up with water. And this pump is the only thing that's pushing that water out before it gets to the level of the floor and starts to come into their basement. Okay. Now, what happens if you're in an area where the sump pump's running all the time and there's a bad thunderstorm and you lose power for 6 hours? What's going to happen? Your basement, that's going to fill up and your basement's going to start to fill up with water. So what do you do then? You get an emergency generator and run your sump pump off of that, or your sump pump's got a little battery backup on it. Now, what happens if your sump pump actually fails? Then you put 2 sump pumps in, they call them duplex pumps. And if the first one fails, the second one's float is a little bit higher and then that one kicks in because you don't want to have the water fill up your basement. So as you're looking for houses, whenever somebody asks me, like a friend or a relative, to look at a house that they're thinking of buying, because I'm an architect, I spend all my time initially in the basement because I'm looking for evidence of water problems in the basement, foundation cracks, the wall bowing in. Because if that foundation is bad, it doesn't matter how beautiful the rest of the house is. Eventually, you're going to have to deal with it. And if the foundation's bad enough, the home inspection report comes back and says, yeah, there's water in the basement and the wall's cracking. The bank won't even give you a loan. They won't give you a loan. They're like, we don't want to pay for a house with a bad foundation. So spend some time, if you're thinking about buying a house, if any of us will ever be able to afford it again, the way the prices are going. But let's just say best case, we all can afford a house. You need to check the foundation before you fall in love with the rest of the house. Okay. Okay, so let's take our break now, and then we'll get started with our practice for the assignment. So let's take a 7-minute break till 10:30, and then we'll get back and we'll learn how to size footings. It's for like the next few weeks, it's a self. At your own pace, hoping to keep up with my assignment deadline, working through the book.
Age.
Okay. Yeah, are you gonna be in class this afternoon?
Yeah.
Okay, well, check.
25. So I'm halfway.
So one thing you may want to ask Josh is that. Say, imagine you're a house designer and my client insists that I have to have a basement. How would you detail it? Where would you put the insulation? Well, how would you do a basement if you had to do one? Because I think that would be very interesting to hear what he has to say. Okay, so let's go into actually how to size column footings. Now, why am I teaching you this? One is that these concepts are used for sizing everything in a building, these basic concepts are like tributary area. So also you'll be able to get a rough idea of how big these things need to be sized on your own projects. And also if somebody else sizes them for you, or you go on a job site and you're like, that footing does not look big enough for all the load that's coming down on, at least you can find out. Is there math involved? I hate to say yes, there is math involved, but don't panic because it's all kind of common sense and the math isn't super complex. And once you understand the procedure, it's not hard. It's just that you need some practice. So that's why we're going to do some practice ones first, and then we'll do the one that's graded. Okay, so let's go ahead and I'm recording here, I think. Yes, I am. And I'm sharing my screen. Yes, I am. Okay, so let's go ahead and start my slideshow. Okay, so we're going to talk about how to size column footings. So as you can tell, I was working in SketchUp just to help you visualize this. And I built a little one-story house here. So there's my basement slab. There's my footing, spreading the load out. There's my foundation wall. But then underneath those columns, I need square footings because they're actually taking a big part of this floor load. So we're assuming that the walls go up here and it's a one-story house and the roof has got trusses that clear span. So there is no roof load coming down, it's just floor load. So what is our flow load? Remember, it's dead load plus live load. So the dead load is the weight of all the floor joists and the plywood and anything that's permanently attached to the floor. The live load is furniture. Maybe they got a water bed. Maybe they're gonna have a party and have a lot of people. So that footing has to be sized to take all that load and to spread it out because that column's only 4 inches diameter. If we don't put a footing under that column, it's going to punch down into the ground because it's taking half, believe it or not, that these columns are taking more load than the wall is because it's being concentrated and it's taking half of this span is going to that beam and column. Half of this span is going to the beam and column. So that outside big, thick concrete wall is only taking a quarter of that whole span distance. Half of it's going into the beam in the center. So let's explain a little bit more detail. So just to show you my assumptions, I've got 2x12 floor joists. So those are these things here. This is my sill plate. That's what's bolted to the foundation wall. This is my rim joist here. Then I've got 2 LVLs, laminated veneer lumber. They're 1 3/4 by 9 1/4 and they're dropped. Those are holding up the floor joists. And the beam is supported by a pocket in the foundation wall. And then it's supported by steel columns. And as you see, underneath every one of those steel columns, there's a square footing. And that's what your assignment's going to be, is to size that square footing. So that's the rim joist again. This is my plate, just another view of that. here's what we have for dimensions. So this outside gray line is my footing down below. I can't see the footing here because it was a SketchUp model. And then this is just my concrete slab. But when we dimension a foundation plan, we don't dimension to the edge of the foundation, we dimension to the edge of the foundation wall. So we don't dimension to the outside of the footings. So let's just go back here. I'm not dimensioning it to the outside of the footings, I'm dimensioning it to the outside of the foundation wall. And in this case, my dimensions are going to the center line of the beams and the center line of the columns. So this dimension, this beam is from the outside of the foundation wall to the center line of the beam, it's 14. And then these are my column locations. So let me just show you. So there's a column here at that 7.4 dimension, and then there's another column here 8 feet away from it, which I forgot to draw on this little sketch that I made. So like I was saying, the tributary area, we're trying to figure out how much of this floor load is actually being held up by the columns. So what happens is when I've got a floor joist that's spanning to a beam line in the center of the building, half of that goes to one end and half of that load goes to the other end. Does that make sense? It should, right? So if I've got something that's being held up on both ways and it's uniformly loaded, half the load's going to go one way and half's going the other way. So here's my floor joist going up and down. Half of that load is going to the foundation wall, half of it's going to the beam. Same on the bottom side. Half of that load goes to the beam, half of it goes to the foundation wall. So you see overall, out of these, this is only taking a quarter of the load from the floor. This is taking a quarter of the load from the floor, and this is taking a half of the load from the floor. So it's very important, right? Because it's taking twice as much as those foundation walls on each side. So that'll make sense, nod your head. Okay. Now, when I've got those beams, and this time I drew the columns in, so my beam's going from wall to column and from column to column and from column to column. So that beam, half of the load goes one way and half of it goes the other way. So let me just show you the next diagram, which I think will help explain how this all works. So I'm trying to find the tributary area. How much of that floor is being supported by that column? So what I do is I take half of the dimensions. So if it's going from the outside of the outside wall to the center line of the beam, it's going 14. So I'm saying that 7 feet is going to end up into that column and 7's going to go to the concrete wall. Same thing happens up here. Half of that 14-foot dimension, 7 feet, comes into the column. So everybody understand how I got the 7 and the 7? All that load inside of that blue box is going to come out into my column. Now, when I go left to right, I go to the outside of the foundation wall to the center, 7'4", and I take half of that, which is 3'8". I take the dimension from the center of the column to the center of the column, which is 8. I divide it in half, which is 4. So I end up with a box that is 7'8" by 14 feet. So everything inside of that blue box is coming in to my column. And in this one, I'm only got 7 feet between columns, so that's 3'6". So that's 7.5 feet times 14. Everybody tracking that part? Anything inside of that box has got to go into my column and eventually it's got to get spread out onto the footing and go into the dirt. So when you do my little practice assignment, this is showing you exactly how to do it down at the bottom here. So where it's showing you this is like the standard procedure that you're going to follow to do this. First off, you figure out this, you can sketch this box on the plan and you figure out the dimensions of this box. And it's always the rule of halves. If I've got a 14-foot dimension, I take half of that. So in this case, it's 14 feet, which is 7 plus 7. And then these two dimensions added up equal 7.67 feet. Does everybody know how I got 7'8" to 7.67? I took 8 divided by 12 and I ended up with 0.67. So I'm converting feet and inches into decimal feet. So then I end up, I made a mistake here. There's a problem. it's supposed to be 107.4 square feet, not 17.4 square feet. So let's look at this green box here, because QCR this for the first time and I see I made a problem. So 7.5 times 14 equals 105 square feet. So then you need to know what your loading is for that each square foot of floor. So I'm telling you, in this case, we're using 55 PSF, and that's what I typically use in houses. 40 PSF is the live load required by code, and 15 is the dead load that's typically used for house floors. So you add 40 plus 15 and you get 55 pounds per square foot. So I tell you in the assignment how many pounds per square foot you're going to use, okay? So I take 105 square feet times 55 pounds per square foot, and I end up with 5,775 pounds. You are going to need your phone or a calculator. I don't expect you to do all this math in your head, and it's good to write it out or type it in your computer if you're working electronically. So now I know how much load is coming down onto that footing. And I know what my soil bearing is, which is, we don't have a soils report, so we're using 2,000 PSF. So all I do is I take that load and I divide it by the 2,000 PSF, and I end up with 2.8875 square foot. So that's the size of my footing. So my footing has to be a minimum size of 2.8875 square feet. Now, if I made the footing bigger, the way I'm pressing on the soil would just go down from under 2,000 square feet. It would get down to 1,500 or 1,000 if I made the footing big enough. Okay, but we're going to size for the worst soil that we can typically run into, which is 2,000 PSF. So now, great. I know I have a 2.8875 square foot footing, but I have to figure out how big do I actually make it in the real world. So we use our old friend, the square root, because the square root does is it says, if you take this number and you times it by each other, it ends up with 2.8875. So everybody know what the square root symbol looks like on your calculator? Let's just pause it here and open up our calculator. I used to have a pen, but on my new computer I don't. So I'm going to open it up and pen it here. So let me just quick pen it here. So there's your square root. So let's try this. 2.8875 square root. So this is 1.69 or 1.699. So on my example here, let's go back to my slide. So I end up with 1.7 when I get the square root. So that means my footing needs to be 1.7 in both directions. It's a 1.7 foot square footing, but we're going to change that to inches. So I take 1.7 times 12. I end up with 20.4 inches square. And then we're just going to round it up to the nearest even inch number. So 21 is not an even inch, but 22 would be an even inch. So I'm going to make that a 22-inch square footing. Now that I've explained it, let me show you a bigger slide, which I probably should have done it from the beginning here. So there's the math again. We figure out the area of the box of our tributary area, and we figure out how many square feet. So this blue box is 107.4 square feet, and the green box is 105 square feet. Then I use my 40 pounds live load and 15-pound dead load. I add those up and I get a 55 PSF total load. And so then I just take every square foot is 55, and I know how many square feet I have, so I just multiply them together. So everybody understand, I think initially how we got that load that's being crushed onto the soil? We're going to do practice on this. I'm not going to just give you an assignment and grade it. So practice makes perfect. And you can have this PowerPoint up while you're doing the practice. Then we divide by 2,000 PSF, which is the load if we don't have a soils report, and we end up with a footing size in square foot. And so the square foot is there in square foot. Then we do the square root, and we end up with that number, which is a 1.72 in this case, inch square, foot square footing. We times it by 12 to get it to inches, and we round it up to the nearest even inch. So I could lecture for another hour and keep droning on, but it's worthless because your eyes are gonna glaze over. We're gonna give you a test, practice, not a test, a practice that's not graded. And this is actually harder than the assignment. And if you can get this done correctly, you'll have zero problem with the assignment. And I'm gonna let you work on the practice in a group. So first off, let me just show you on Blackboard the difference between the practice and the assignment. So if we look at the in-class practice, those of you that are remotely, I do have the key here. If you're in person, I've got the key here for you to check. So let's just look at the in-class practice one. Okay, so I'm gonna have you, I've given you dimensions. I'm gonna have you size these footings here. So let's get it full screen and get it bigger. And I'm gonna give you a hard copy to work off of. So if I'm figuring out how much of this joist, so my joists are going up and down on the screen, my beams are going left to right, those are the dotted lines. The little circles are my columns, and the dotted box is my footing. If I've got 12 feet center line to center line, how much of that 12-foot span is going up to footing 7? 6, right? Half of 12 is 6. If I'm going 7'4" plus 8 inches to the outside of that wall, that's 8 feet. How much of that 8 feet is coming into the footing? 4. So we're always doing half. Now let's work left to right. If I'm going from the outside of that wall to the center line of the footing, it's 11'4" plus 8 is 12. How much of that beam's load is coming into footing number 6? If it's 12 from the center line to the out, what's half of 12? 6 feet. Half of 10 is 5 feet. So what I'm going to suggest you do is you just go ahead and draw your little boxes around for the tributary area and write the dimensions on the box and then multiply them together and then write the square footage of the box. I'm going to give you a quick peek on the key so that you can see how I would recommend to do this. See, so what I do is I just quickly draw a box and I draw the dimensions in and I multiply the dimensions and I make the square footage. And then I do the math the way the PowerPoint shows over there. So I'm not going to let you memorize that, but that's how I would go through and do this practice. Just to show you that the actual assignment is easier. I used to give the practice easy and the assignment hard, and that didn't work so good. So I'm going to give you the practice easy because the practice is low stakes and you're working in groups and you'll figure it out easier that way. The actual assignment drawings are much simpler. Okay, so there's 2 of them in that little house and there's 3 of them in that little house. That's the one you're going to be graded on. So what I'm going to ask you to do is I'm going to divide you up into groups of 3 and work on this together. When you all are in agreement, you understand what you're doing, maybe do one and check it and then do the other ones and then check it, check them all. But when you got this done so that you think, yeah, I can do this, I've got this, then come up and I'll give you the real one that you can do for the grade. Okay, and this is due start of class on Thursday. I think I've given you enough time to get it done in an hour here. And if not, at least you'll have it done and then you'll be able to do the real one on your own time. Okay, so I'm going to pause my recording here. And those of you that are on remote, you can just do this on your own and check the key on the one on your own. If you do have any questions, if you're working at home, obviously I'll answer them now, or you could send me an email and I'll answer them later. So let's pause and stop the recording here.